Okay, the only other problem type on tonight's homework outside of working with convolutions to turn them into little ht and pull them out of big HT, the only other kind of problem is solving integral equations. Convolutions are frequently used to solve specific kinds of integral equations. Integral equations come as a result of a function being contained both inside and outside of an integral as part of an equation. They're very similar to differential equations in that frequently these are written as solutions to differential equations and they contain an integral. Well, clearly, without knowing what y is, this is a hard equation to solve. But what we can do is use the special form of this integral in order to turn this into an equation that we actually have an idea how to solve. Recognizing that this guy right here is the definition of a convolution. It's the convolution between the function y of t, which is already sitting here, and the function sine of t. So that's what I'm going to do. I'm going to just rewrite the equation as y minus y convoluted with sine of t, and then that whole thing is equal to t. Well, this becomes an equation that we can pretty easily solve, because a property of convolutions we know is that if I go to take the Laplace transform of this entire thing, I'm going to take the Laplace transform of y convoluted with sine t. And of course, we did all this work with convolutions so that I know the answer to this question. The Laplace transform of convolutions is the product of the Laplace transforms of the individual functions that are convoluted. So this will be capital Y, ys, times the Laplace transform of sine t. And that, of course, is 1 over sine squared, s squared plus 1. So don't think we're cheating here. We're not saying, hey, the Laplace transform of a product is the product of the transforms. This is a convolution, and we pulled it out of the equation because that was its form. So keep in mind, we're not cheating here. We're not saying that if you've got the product of two functions, you can simply write that as the product of their Laplace transforms. But these are convoluted. So rewriting the equation looks like this. This will be the Laplace transform of y minus this bit here is going to be the Laplace transform of y times 1 over s squared plus 1. And then now all that equals t. Well, we can do some work here on the left-hand side. This is going to be y factored out. 1 minus 1 over s squared plus 1 equals t. If I put 1 as a special form of the number 1, s squared plus 1 numerator denominator, that's going to make y s squared over s squared plus 1 when I put all that together, and that equals t. And then, of course, all the way from the beginning, we were supposed to have applied the Laplace transform to t. Remember, that's 1 over s squared. So that should be 1 over s squared all the way down, because from this line down, we were in the world of Laplace transforms. Okay, so at this point, we invert and multiply so that y is going to be equal to s squared plus 1 divided by s to the 4th. And that's equal to 1 over s squared plus 1 over s to the 4th. And if we look up on our table of Laplace transforms, little y of t, the solution to the original integral equation, is going to be equal to t, which is the inverse Laplace transform of 1 over s squared, plus t cubed over 6, which is the inverse Laplace transform of 1 over s to the 4th. So there it is. There's the solution to the integral equation, and we were only able to find it because we could recognize that this was a convolution of y and sine t. And so from that moment on, we could use Laplace transforms to solve the equation.